Hi, everyone. Welcome to our session. My name is Basak, and together with my colleague Maria, we will talk about model traceability and reproducibility. Before we dive into the problem and the solution, let's have a look at what type of organization we work at. We are working at Ahold Delhaize. It is one of the largest food retailers in the world. It has 19 brands in different continents. It's a very complex structure, as many other companies of this size. Maria and we are working at Global Support Office. It is a central unit that supports brands from different angles. It can be legal, it can be finance, it can be HR. We are in the digital department and we support brands from data science perspective. Some brands do have very advanced data science capability. They have big teams. Some brands do not have any data science or MLOps capability. So we help those brands who are in need of either data science or MLOps help, MLOps need. So while we started working at Ahold Delhaize, we started also observing some issues that are happening in the brands that we support. Because things are not always going right. Examples. We have a personalized offer model. It gives weekly personalized offers to our customers based on their purchases, previous purchases. One week, we realized all of our customers got very expensive gin offer, not really relevant to everyone, and we couldn't really identify what was the reason, because we were not able to go back to the model artifact or the code that is responsible for that prediction. Another example, we have a cross-sell model running on our e-commerce websites. It's a real-time inference model. When our customers are shopping, while they add new products to their baskets, this model suggests them to add more items. One week, our customers kept seeing only plastic bags as suggestion to add their baskets during their online shopping, and we actually couldn't understand why. We wanted to go back to the code and the model artifact that is used. It took us a lot of time and effort to investigate this problem, and all these things can affect our customer journey in a negative way. So if we frame the problem, when things are going fine, it's all peace. But when things are going wrong, it would be very difficult to fix the bugs. It would take so much time. It would also take so much time to find the relevant code for prediction to actually investigate further. And if we're not happy with the current model, it was not really possible to revert back to the previous model as we were not able to trace back. So as a solution, we said, let's implement traceability and let's embed it in our design. So what is traceability? Traceability is for any given machine learning model deployment, it is possible to look up unambiguously the corresponding code and commit on Git, the infrastructure used for training and serving, the environment used for training and serving, corresponding job run, and the machine learning model artifact. So we wanted to implement this in our solution design. But traceability is not limited to any certain tool or any certain solution architecture. For each component, there are multiple tools, multiple software available in the market. We just needed to collect what we have in our organization for version control, CI/CD, orchestration, model registry, container registry, compute, and serving. So as you see, there are many examples that can be used for each component. In our organization, we have the followings. So we use GitHub as our version control. We use GitHub Actions as our CI/CD. We use Databricks workflows to orchestrate our jobs. We use MLflow for model registry. We use Azure Container Registry to register our Docker images. And we use Databricks jobs and clusters as our compute power. And we use Azure Kubernetes services for serving our real-time inference-based models. So with this, this is our solution design. We have a data lake, which is blob storage. And we get our code from version control, which is GitHub. and we put it in our Databricks compute power as a job. It's a training job, and we store our artifact after training is completed in our model registry ML flow, and we create our Docker image with the model artifact, and then we deploy our APIs using Kubernetes for serving purposes. So this is our solution design. And traceability is implemented on top of that. So what we do is we connect GitHub commit hash, Databricks run ID, MLflow run ID to each prediction generated by the model at each API request. Before we dive into the solution, I also like to highlight that we have two different environments. We have pre-production and production. They are the same architecture with different workspaces. From pre-production environment, we only have read access to production data, which allows our data scientists to develop their models with real data. This is, again, for our company, for our organization. It can be different for in each organization to have how many different environments or workspaces. For cost-related reasons, we kept it as two environments. So Maria will dive into traceability by design in 5 steps.
I want to highlight first that we use Databricks as a main compute for training our models. And when we look at Databricks workflows just as any orchestrator you have, like Azure Data Factory or step functions, it can be defined in JSON format. So any Databricks job is defined as JSON. So if you go to Databricks workspace and click on any job and look at job details, you can see a representation of that. This is important because we can use it to pass certain things to this job JSON definition that can help us further in doing traceability by design. So if we are looking at all these steps that we mentioned, step 1 would be how can we make Git SHA available inside the Python script that runs on Databricks? So to catch Git SHA, we use GitHub Actions. It is available in GitHub Actions. Then we have that as environment variable in GitHub Actions, and we use this information to modify our job definition at inside GitHub Actions. So basically, the output of it would look like Git SHA passed as environment variable inside our job, which will make it available for us to catch it and pass it further. So the step 2 would be how to make run ID available inside the Python script that runs on Databricks. So that is not that trivial. There are multiple ways of doing so. So for example, if you work with Databricks, you are familiar with dbutils library, most probably, that can be used to catch run ID inside a Python script that's running on Databricks. But we don't want to use dbutils because we want our script to be runnable anywhere. dbutils is only available on Databricks, so locally it's not possible to use it unless you use some kind of connector to Databricks. But if you just want to run some tests, you would have to adjust your code a lot. And we don't want our code to be adjusted to run on any environment. So it should be the same code that can run pretty much anywhere. So then we looked what are the other possibilities. So Databricks provides a nice feature called task parameter variables. So these are the variables that can be passed to your Databricks job definition, and those will be filled at the moment of run. So the examples of such task parameter variables are job ID, so it's a unique identifier assigned to a job, run ID, unique identifier assigned to a job run. If you have a job with multiple tasks, then you need to have parent run ID as unique identifier for run of your job. And there is also variable like task key. There are more things that can be used as task parameter variables. For example, if you have secret scopes defined in Databricks, those can also be passed as task parameter variables. So because we pass job ID and run ID as Python parameters, then those can be readable inside our Python script that we run. Next question would be, when we have this Python script where run ID is available and get_SHA is available, we need to register a model in the ML flow so that it can be retrieved later on by specific run ID. Run ID is pretty much unique, so get_SHA is not that important then, but it is important for traceability so that we know what code exactly, don't have to look it up, but it is sufficient to retrieve it just by run ID. So as I mentioned, run ID and job ID is now available as Python parameters for your Python tasks, so it can be retrieved using argument parser. So basically, run ID and job ID are now available inside the Python script. And then we want to tag our run in ML flow by using this information. So we create some tags when we register the model. It would be commit hash, job ID, run ID, also ML flow run ID, which is different from Databricks run ID. Things like experiment ID and maybe some extra things you want to pass. So we use register model function to pass those tags that are defined here. And when we do so, then we can go back to the Databricks workspace and look how our models are registered. And then you see that all this information is available there. The commit hash, job ID, run ID, experiment ID, and experiment name we passed in this case, which makes it actually searchable, which brings us to the next step. We want to embed the model into a Docker image. So we need to download it first in our GitHub Actions to be able to pass it to the image at the build stage. Of course, you could argue, why do we need to embed the image into the Docker? Why do we need to embed the model into the Docker image? Well, in our case, it's the connectivity from Kubernetes to ML flow is not always straightforward due to security due to security restrictions, but it can be done differently if you have a different use case. So in our case, we want to always embed model into the Docker image. So how do we do so? As I mentioned, because we have certain tags like Databricks run ID available for all our models that we register, it makes it searchable. So in MLflow client, you can search for model version that is corresponding to a particular run ID. And then with model artifact repository, you can actually download this artifact using this version that you just have found. So which makes it possible to download the artifact in GitHub Actions and pass it to the Docker image at the Docker build step. So then when we have a Docker image available in Docker registry, we also tag it with get_SHA and run ID. We want to make also get_SHA and run ID available inside the Docker that is used to serve our API and provides a response that contains get_SHA and run ID as well. So to deploy API to Kubernetes, it's possible to pass environment variables in the deployment manifest. So deployment manifest is also modified in GitHub Actions, where run ID and get_SHA are available. And we pass this information to the manifest, and when it's deployed, those are retrievable inside our app using as environment variables. So basically, we then return, when we return the prediction, we also return this extra information. You may argue, why do you need it? Why do you need to do it this way, that it's available in response body? So in our particular use case, our APIs are not faced directly by the clients. They are used by front-end team, and it is very handy to know for them in case we do A/B testing then the API they call will produce different responses with Git SHA and run ID, which will be different for model A and for model B. So if they start to see a weird performance for one of the models, they can tell us exactly what run ID was producing those weird predictions, and we can fix it. So it makes it much easier to communicate with the team and makes our life in the end much easier. Because we implemented all these 5 steps and everything is traceable from the beginning to the end, it also actually makes it very easy to do the rollbacks. So the rollbacks in our case is triggered manually on workflow dispatch, because that's something that you don't do that often anyways, and that's something that you typically do manually. So if you can then roll back to the previous to the specific Docker image, because we know what run ID and what git SHA it has in tags. And if no input is provided to a specific Docker image, we can always retrieve the previous Docker image, because we know what version it is in MLflow that we use currently. Let's say version 3. We know that the previous will be version 2. And version 2, we know what git tag and what run ID it has. And because those information is available as tags in our Docker image, we know what Docker image to use here. So in this case, rolling back it becomes very easy. So to come back basically to our solution for traceability, there are these 5 steps that go from version control in GitHub to compute in Databricks. Then we store artifact in model registry. When we have this available, we embed it into Docker image and store it in Docker registry, and then we deploy it on Kubernetes. And because those variables are available as environment variables, we can also access it in our app and provide it in the response body. Thank you for your attention. That was our presentation on traceability and reproducibility, and looking forward for your questions.
Thank you very much for this informative presentation. Thank you. We are more than happy to take any questions.
Yes.
There are no questions yet, so we can
Okay.
give it a couple.
Well, I can imagine that many people have comparable experience with that it's hard to trace things back, and I think that is quite helpful. How do we manage the storage archival of the Docker image? There is a question. So what do we mean by this question exactly? So we store all Docker images in our ACR, and there is also cleaning procedure that we want to implement at a later stage, so that all Docker images will be removed, and only last 3 or so are kept. That's something that we are planning to implement that is currently not implemented. But I think it's important to have this cleaning procedure for your Docker images and for all your artifacts, because it costs you storage and it costs you money in the end if you don't do so. The same goes for logs.
Yeah, ACR is Azure Container Registry. And so far our models are trained either weekly or daily, which is now still manageable to keep the images.
Awesome. We have another question.
And do you store, retrieve the metadata for traceability in a structured way? So I'm not sure what is meant by structured way. So the way how we store the metadata, well, the metadata is basically the tags, I guess, the tags for the model artifacts. So those are quite easy to retrieve using this Malfo client, but we don't store any information like this in a database or anything like that. Or in the logs we have some of this information as well, but it's not stored in a table or database or anything like that.
We log our response with prediction and with necessary tags like run ID and git hash when we have API requests. So those are logged.
Yeah, and we need this information also for A/B testing, because when we do A/B testing, we need to know what requests and responses were corresponding to what model, and then we can connect it back to the data in the data lake and tell what model did better than the other.
Great. Thank you for answering this question. We still have some time for other questions.
Maybe as a feature work, we also want to implement certain traceability on data versioning, because we retrieve data from our data lake, and it is data engineer's responsibility to put data there and make it available. But we do not have yet the control on which data version is used in our model. So that's our next step, to also have visibility and traceability on data versioning.
No more questions came so far, but we still have time.
Maybe we can tell in general what we are trying to achieve in our organization. So we are part of the central unit, as we were explaining. We are part of general support office. And we see that a lot of different brands have the same needs. So the solution we presented, that's something that is implemented in reusable CI/CD pipelines that pretty much everyone can use. And they are importable workflows that we provide as a service to the brands. And those brands can also contribute to what we do. So basically, this traceability, that's something that can be implemented. If someone had a notebook, a Databricks notebook, we could make it traceable within an hour based on the pipelines that we provide.
Okay, thank you. There is a question.
Yes. So the question is whether we also thinking to equip data science team to take ownership of the MLOps work. So that's exactly the purpose of what we are doing. So the pipelines that we provide, data scientists have all power to do deployment themselves. Of course, there are some guardrails, so they have to create a pull request and follow all the processes that are that everyone knows from software development. But they have all the power to deploy themselves. So basically, they don't need machine learning engineers to do this for them, and we try to empower data scientists. That's the goal of what we do, because the brands that we work with, they don't have their own machine learning engineers often. And we don't want anyone to be dependent on us, because we need to support a lot of different teams, a lot of different projects, which means, that's the only way for us to give the ownership to the data science teams.
So what we are trying to achieve is more to provide them a golden path, which is basically how to do certain things, how to deploy models, how to make sure traceability is in place. And we provide those tools to data science teams within the brands that we support, which also makes things more reusable. That way, the data science teams themselves can actually deploy models. Thank you for the question.
Awesome. Thank you for answering.
Yes, so brands are sharing and reusing infra. Well, not really. So we have different brands, and there is also a central platform team for some of the brands, and those have reusable infra deployment. So basically, the infrastructure is deployed in the very same way for all those brands on the platform. And because it's all shared and it's all set up in the same way, the workspace is shared typically across multiple projects. And we have organizational secrets in GitHub that they use, where service principal credentials are stored. So in that sense, it is made super easy for data scientists to use those pipelines without thinking about any of these technicalities behind it.
So they not really share the infrastructure, but the infrastructure are deployed for each brand in the same way. So they actually have all these components in common, which makes our pipelines reusable, of course, because they're implemented in a certain way to create interaction between different components.